Let's suppose that you work for a soup company and they've given you a task to design a soup can that can hold 300 times pi cubic centimeters of soup. This is really an optimization problem. Your goal is to design a soup can using as little metal as possible, which nevertheless holds 300 pi cubic centimeters of soup. Okay, less dramatically, you're really being asked to produce a cylinder with a given volume. I want the volume of the thing to be 300 pi cubic centimeters, and I want you to minimize the surface area, right? This thing's got a side and a top and a bottom, and I want you to minimize the surface area for a given volume. Probably helps to review a little bit of the geometry that goes into this problem. Here's a picture of a cylinder, right? And it's got some height that I'll be calling h and a radius that I'll call r. And the volume of this cylinder is pi r squared h. Right? Pi r squared is the area, and I'm multiplying by h to compute the volume of this disk dragged through space. What's the surface area of this cylinder? Well, 2 pi r squared counts the surface area of the top disk and the bottom disk. Each of those has pi r squared for their area. And the curved part of this cylinder has area 2 pi r h. Okay, let me draw a picture of my soup can. So yeah, here's a little picture of our soup can, and you see I've labeled the relevant sizes. The height of the can and the radius of the can is what I'm trying to figure out. Now, what is it that I'm trying to optimize? So I'm trying to minimize the surface area. Here's that formula for the surface area of this can, and I want that surface area to be as small as possible. Of course, if I wanted to make that surface area as small as possible, I just make a really tiny soup can, right? But there's a constraint. Well, the constraint is that that soup can has to hold 300 pi cubic centimeters of soup. So I'm trying to make this quantity, the surface area, as small as possible, subject to the constraint that the volume of the soup can is in fact 300 pi. And I should also point out that the radius and height had better be positive, otherwise it's kind of nonsense. This thing that I'm trying to optimize really involves two variables. It involves a height and also a radius. Yeah, this is some bad news, right? The quantity that I'm trying to minimize involves two variables, involves r and h. And calculus, as we've been setting it up, only works for understanding how a single variable changing affects something else. So I need to rewrite this function of two variables as a function of a single variable. So here we go. Let's take this constraint and let's solve for h, right? And if I start doing that, well, h is 300 pi over pi r squared, and I can cancel these pi's, and I'm just left with h is 300 over r squared. So for a given radius, this is how tall I need to make the soup can to guarantee that the soup can holds 300 pi cubic centimeters of soup. Now once I've got an equation for h in terms of r, I can use this to rewrite the thing I'm trying to minimize just in terms of r. So here we go. The thing I'm trying to minimize now is 2 pi r squared plus 2 pi r times h, but h, in order to satisfy the constraint, is 300 over r squared. And now I can simplify this a little bit further, right? I've got an r and an r squared here, so I can get rid of this square and get rid of this r, and then the thing I'm trying to minimize is 2 pi r squared plus 2 pi times 300, which is 600 pi, divided by r. So this is the quantity that I'm trying to minimize. Now that I've got this thing written as a function of a single variable, I'm really tempted to do the fifth step here, apply calculus, right? If I got a function of a single variable, I could differentiate, find the critical points, figure out where the maxima and minima occur. But before we dive into the calculus side of this problem, let's just think about some creative solutions to the soup can issue. For example, here's a little model of the situation. Here's the sun, here's Earth, and here is my new plan for soup cans, right? Really big radius, really tiny height, right? Even if r is, 100 million miles, I can make h small enough so that this soup can contains exactly 300 pi cubic centimeters of soup. Well, what's the surface area in this case? Is this a really good choice for a soup can in terms of surface area? No, right? If I make r really big, admittedly this quantity, 600 pi over r, which is measuring the curved area, that'll end up being very small, right? But 2 pi r squared, when r is really big, this quantity, the amount of metal in the top and the bottom of the can, is enormous, right? So this is not a great choice for soup cans. So having the soup can shaped like a giant pancake is a terrible idea. But what if I went the other way? Here's a piece of wire. What if I made the soup can really long and thin like this piece of wire? Well, here is that long, thin, wire-shaped soup can, right? Even if I make the radius of my cylinder very small, if I make it long enough, then the soup can does hold 300 pi cubic centimeters of soup, right? And the question is this a really smart choice to minimize surface area? And no, it turns out that if r is really small, that's really not all that helpful. Yeah, if r is really small, then 2 pi r squared is really small. I don't need very much metal on the top and the bottom of the soup can. But then 600 pi over r, which is how much metal is on the curved part of the soup can, this quantity is going to be enormous. So really we see that these two things are competing against each other. A small value of r isn't really very helpful, and a really big value of r isn't very helpful. So our creative solutions didn't quite pan out. Let's do some calculus now. Okay, so I'm going to think of the surface area as a function of a single variable r, right? Here it is. F of r is 2 pi r squared plus 600 pi over r, and I'm going to differentiate, and here's the derivative, right? I differentiate 2 pi r squared to get 4 pi r, and I differentiate this number divided by r. Well, 1 over r is negative 1 over r squared, that's its derivative, and then I multiply by 600 pi. So this is the derivative of this. Now I need to find the critical points. Now, remember what critical points are, right? Critical points are where the derivative vanishes or where the derivative doesn't exist, right? The function is not differentiable. This function, though, is differentiable on its domain, right? You might worry when r is equal to 0, but that's not even in the domain of the original function, so I don't have to worry about that. All right, now I just got to figure out when is the derivative equal to 0, so I'm trying to solve this. I'll add 600 pi over r squared to both sides, so 4 pi r must be 600 pi over r squared in that case. I'll multiply both sides by r squared, and I'll divide both sides by 4 pi, and I'll get r cubed is 600 pi over 4 pi. The pi's cancel, and 600 over 4 is 150. So r cubed must be 150. In other words, r is the cube root of 150. This is the only critical point. Now that I found the critical points, what about the endpoints? Well, the endpoints actually aren't really valid in this situation. One of the endpoints might be when r is equal to 0, but in that case the soup can has no volume, so I can't satisfy the constraint. The same thing happens when h is equal to 0. In that case, the soup can again has no volume, so I can't satisfy the constraint. So I don't have to worry about the endpoints because they're not in the domain that I'm considering, but I do have to worry about the limiting behavior when r is really big or when r is really small. So we actually already handled the limiting behavior, right? We've already considered the situation when r is really small. That's the situation where the soup can is like a long, thin wire. And we checked in that case the surface area is enormous, right? If r is small enough, the surface area can be as large as you like and still hold 300 pi cubic centimeters of soup. We also considered the situation when r was really large, right? When r was really big, we had this sort of flat pancake shape for the soup can. And in that case, we again saw that if r is big enough, the surface area can be made as large as you like while still having that soup can contain 300 pi cubic centimeters of soup. So the only thing that really remains is this critical point, and if you plug this critical point into the original function, you get this as the resulting surface area. If you build your soup can with a radius of cube root 150 centimeters and your height, whatever it has to be, in order to guarantee that the soup can contains 300 pi cubic centimeters of soup. So how does this turn out? What's the best shape for a soup can? So the best case for your soup can is to use a radius of the cube root of 150. And you can see that from this graph. Here I'm graphing the surface area for a given radius of soup can containing 300 pi cubic centimeters of soup. And you can see that the graph goes up towards infinity here and up towards infinity there. And that's exactly the situation where the radius is very small or very big. The derivative is negative and then positive, right? The function's decreasing and then increasing. So this value really is a local minimum. And in fact, this is the global minimum of this function, right? And that's why this is the best choice for your soup can. Is this really a legitimate application of calculus? Well, here's a task to think about, right? Go out, find some soup cans, and check them. Are they really building soup cans in order to minimize the amount of metal that it takes to manufacture the can? Or perhaps there's other issues involved in manufacturing soup cans.